Rotary encoders are people's favorite component more often than not, and with good reason. They feel really good. The most common ones that you will see are these indent rotary encoders, and each time you turn them, it has a very soft click almost to it, and this is a 20 indent per rotation rotary encoder. And you really cannot use these unless you know coding, or if you know how to hook these up to microprocessors. And I'm really not into that type of electronic work yet. I really enjoy just using hardware, and honestly, these things are really hard to do, and there's not very much information out there on how to make a hardware interface with a rotary encoder so that you can use these to communicate as a microcontroller would, but without having to do any of the fancy computer stuff. So we're just going to go right into it. I did not purchase the ones that have a breakout board on them already. A lot of these rotary encoders will already have the pin outs labeled and have your pull-up resistors, as well as your debounce capacitors in there. And I bought them like this because I had no idea how these things work. So we're going to go ahead and start from the bottom up on how to build a breakout board for the rotary encoder. So let's start off with what's actually going on inside of the rotary encoder. So starting with the easy side, where there are just two pins. On that side, it controls the push button action on the rotary encoder. And all that is just a momentary switch that is normally open, and you close it for just a moment as long as you are pressing the switch down. So here's my really funny drawing of what's going on as far as the encoding part of our little device here. And so when you turn the knob, what you're doing is turning these wipers here across two contact points. And we're going to call these contact points A and B. And each of these are connected to our left and our right pin of our rotary encoder. And so we're going to call this one A, and we're going to call this one B. And the center pin here, or our C pin, or common pin, that one's going to be connected to our wipers that we're moving across these contact points. And this is called the indent rotary encoder. On each indent where it stops moving, it is an open connection in between the wipers and the contact points. And so as you move it in between each indent, these wipers are coming in contact with A and B, first A and B as you're rotating it in a clockwise fashion, or first B and then A in a counterclockwise fashion. And so what this is encoding is whether you are turning the knob to the left or to the right, you will get a connection in between our center and A first, or our center and B first, depending if we're going clockwise or counterclockwise. That's the basics. Obviously, there's going to be way more wipers inside of this than just what I'm showing here. Next, we're going to show exactly how you wire this up so that you can start using the data made from connecting these, because just using these as a switch from alpha to Charlie or Charlie to Bravo, it's not really all that useful. So let's put some real basic passive hardware on here. So first off, what you want to do is connect our wiper here to ground. And so that's going to come up and go to ground for us. And so what that does is that each time the wiper connects to A and B, it's getting shorted out to ground. Now we need to provide a source of power to this circuit so that we can register either an on or an off position, because eventually we're going to be using this encoder to be decoded by further circuitry along. So we're going to pull these high with a pull up resistor, and this just needs to be enough to not cause any problems of drawing too much current through the short circuit to ground as the wiper makes these connections. So I'm just using a 15K ohm resistor right here in connecting our A and our B lines to our positive voltage is where we're going to put these. And as I'm going to be working with digital circuits or logic gates, we are going to be using a 5-volt system. And so now, when we rotate this encoder, what's going to happen is that we're going to have a positive voltage in this wire until it makes contact, and then it's going to be shorted out to ground, and we're going to go from a equivalent 1 to a 0. So in order to visualize this a little bit better, let's toss some LEDs into the circuit here to show us when our data is either high or low. And so by just simply putting these in here as we turn it, our encoder, we'll easily be able to see whether we're turning it to the left or to the right. So the next thing that we have to address is going to be the fact that this is an imperfect connection that's being made, and it is not going to look under an oscilloscope the same as an on and an off clock pulse would look in a digital sense. So when our clock is going to be coming up and down, or when our contacts are going to be made, we want them to look nice and crisp for our digital circuits. However, when we are going to be turning this encoder and making these connections, as it's a mechanical connection, it's going to be very imperfect, and we might get a lot of noise in our voltage where it's making connection and then not making connection before we actually get our signal that we want to process. And with all of this, it's going to cause a lot of glitching within this very small amount of time within our circuit, and it's going to cause a lot of problems down the road. And so in order to avoid that, all we have to do is put a small capacitor in between our positive rail here that's going to be shorted out to ground, making the connection, and to ground. And what this allows is for the capacitor to absorb the first noisy bit of contact. We're going to pick a 0.015 microfarad here. And this just works really well for me as far as the timing of how much noise I get out from a regular connection time of turning the switch. But you don't have to use this exactly. Just something around a 0.1 peak or microfarad is going to work well for you. So now that we have this part, this side of our encoder with our hardware installed, we're going to focus on the easy side here, which is going to be our push button contact. And we're going to basically just copy this right here, this very small simple circuit. So it's basically just the same thing that we had up here, which is going to be an LED showing us whether or not we are making a contact or not through our switch. And I'm just realizing now that I put in my LED backwards here, which silly me. Let's go ahead and rectify that real quick. It's going to be a dark LED. There we go. But it's basically the same thing that we have going up here, just a debounce capacitor as well as an indicating light. So now that we have this we're going to go ahead and toss this on a breakout board, and it's going to look something like this. And so this is going to be on the bottom. You can see our current limiting resistors right here, our 215Ks, as well as our 100K right here for our push button switch on this side. And then our debounce capacitors all going to the ground pin. So let's go ahead and put this on a breadboard. And this little LED here, I didn't put onto the board just because I didn't think it was absolutely necessary to have an indicator that you push this down, just because it makes such a solid contact when it pushes down. So I'm going to be powering this with a 9-volt battery just through LM7805 power 5-volt power regulator. So as you can see, the lights are on standby, just on always, because in between the indents, these wipers are not making contact, shorting it out to ground. It's simply remaining pulled up by these current limiting resistors. But as you will see, when I rotate the knob, one will go out first as I'm rotating it clockwise, then the second, and then this will come back on, and then that one. And so as I rotate it clockwise, you can see that B is going to be shorted first, and then A, and then B will be pulled high again, and then A will be pulled high again. This way you can have a left and right encoded signals on two different wires. And then for the push button, it's the same idea. When the contact is being made, it shorts out our signal, and when it isn't, it's pulled high. So now that we have made our breakout board for a rotary encoder, the next step is going to be turning these signals that we're getting from a positive to a negative pulse, from a negative to a positive pulse, via some hardware and logic chips. So stay tuned. I'm going to make another video explaining that and taking this further with my Arduino-less code-free rotary encoder project. Thanks for watching.